So this is the idea. You take an image, you can turn it into black and white, get this set of values for the image into a matrix. So each and every pixel is a value that you can map. And then you can just see these set of input values over here. Does this make sense to you guys? And you can normalize it. That means to make them between 0 and 1. And this is what the input looks like. Any questions on this? So we'll come back to this here. So how does a neural network learn? So the idea is, to start off with, we initialize some random weights in the neural network, some random values. That's what we initialize here. These are just a set of random values. Random values between, any set of random values. So you guys remember that what this 0.2 is based on was based on what these weights are. Did you guys remember? Like what this value is based on what these weights are. And what these values all are, what weights are. Like, so think of it like in a gym class where you have a set of, you have rope and you have to jump from one hula hoop to the next hula hoop to the next hula hoop. So it's a similar idea. We're here to go from, this is the input, this is the data you're given. It's a bunch of pixels. And to go from this neuron to the next neuron, you need to know what these weights are. But what are these weights? You guys also wonder what these weights are? So these weights are things that the neural network is trying to learn. It's trying to estimate what are these weights. So that's a huge part of training. Training is trying to figure out what exactly these weights are here, to go from one to the next layer. So if we don't make mistakes, we don't learn. So the first step that we do is we just give some random weights. Imagine if I don't know what you guys know. So to be able to go from this input to the output, we gave in an input. We want some output. So we just need to put some random numbers here for now. Does that make sense? We need to put in some random values so that we can go from an input to a hidden layer to the next layer to the output. So I don't even know where to start. So I'm just going to randomly put some numbers. But I should probably, maybe I could try to use some method to choose these weights, because it's almost like I don't know where to teach you guys, for instance, like if I'm your teacher for the SATs or the ACTs, I don't know where to teach you guys. I'm going to give you guys a practice test. Hopefully you guys do your hardest on it, like treat it like the real SATs, for instance, and then I'm going to see how you guys did, and I'm going to figure out where do I start from. So I'm going to just randomly hope that you guys do your best, and I'm going to try to choose some good weights to start out with. Eventually we might get there. Like if you guys just choose to like bomb the practice SATs, I might not think you guys know what fractions are. And then we might spend an extra couple of weeks talking about fractions and stuff that you guys actually know, right? Because I won't know. So it's in your best interest we'll get there eventually. It just might take a longer time. So you might want to choose, you might want to choose a really good weight. That way it takes less time for training overall. It will get there, but it might just take a long time. And for neural networks, this can be days, weeks, months, or even years. So you really want good models overall. Like you want to choose good weights. So you just randomly choose something just to get started. Like I give you guys a test just to see where you guys are. What do you guys know? What do you not know? Then I go back and I adjust. So I just randomly choose some values. I randomly choose some values for these weights. And then I'm like, just let it go, let it crash and burn. If it crashes and burns, so be it. So I just put in some random weights. So I didn't want to show all of those values here, but you can imagine these are all like just random numbers. Then I have the prediction made here. I make a prediction with these random weights. Obama, I predict 40% for this image then. Not Obama, I predict 60%. So what will I go with?
Well, the system would go with the 60%
Yeah. And so
for a human.
do you think it's a good model? No, it's like majority. If I have like five classes and like whichever one is highest. So if the two classes, like if I'm predicting happy, sad, mad, angry, I would have like five of these, the five emotions. And the one that's the highest, I go with that. So here, there are two outputs. So it's just going to have two of these nodes, right? The two outputs, either you're Obama or you're not Obama. No number of classes that there are, the number of outcomes, those many nodes there will be. Like if there's happy, sad, angry, neutral, something else, and there'd be like five if there are five emotions here. So this is not good. So I just randomly gave some weights, right? Maybe you guys crashed and burned the practice SAT, but at least it helped me to know where to start, right? Like you guys, maybe you guys didn't do so great, right? But that's why you guys are here. You're here to learn, right? I'm here to train you guys, right? For instance, for SATs, for instance, or for the ACTs, like you guys took a practice test. Let's say, hopefully you won't, but like let's say you bombed it, right? You just did whatever you did, guessed on stuff that you didn't know. Like I just randomly made some weights, right? It's the same thing as you randomly guessing on stuff that you don't know. Just so you can finish the exam, right? I just want to see what all you guys know. If I put you in a situation for the SATs or ACTs, how would you guys do? So you randomly guessed even on stuff you had no idea on, just so that you could go and complete this test. You guessed along the way on stuff. And then maybe it didn't turn out so great. Like you guessed not Obama. Like in the end, like it's like the model predicting not Obama on a photo that's Obama. Like it's not a good model. But I know where I have to go. So this is 0.6, not Obama. So what should I do? What do I want this to ideally be? Remember, these can be between 0 and 1. Like what do I want this to be? Like what would I have wanted it to be?
High percentages like 0.9,
Yes.
0.8,
What would be the best case? The best.
0.99,
Yeah, like
something like
1
that.
and then 0.
Yeah.
Straight up 100% and 0%. Ideally, I would want that to happen where this is like, or this is the majority, at least like, 0.51 and above, but if it's so close, then that's also not good. Like if it barely recognizes, like if you guys pass your driving exam and you just passed it, like would your parents or guardians feel so good about giving you the keys, or if you guys did pretty well? It's like that idea. Like if your model just 51% said Obama, 49% not Obama, I'm not going to be that thrilled about it, right? I'd be like, it was so close to saying not Obama. It's like, I passed. I got a driver's license. Your folks are like, you do know the driving instructor did put down, like you were like crying that like you were gonna fail. So of course they felt bad and let you pass, right? Or something like it's almost like a very boundary condition where like you almost could have failed, right? So like you're not gonna be too thrilled about something on the boundary. So the idea is you want this to be say 100% Obama and 0% not Obama as much as possible. But you now know that these values, but whatever this value is, it comes, this 0.6, and the same thing for 0.4, this comes from this. It comes from this neuron. It comes from this neuron. It comes from this neuron. Comes from this neuron, like whatever values it's getting. And each of these neurons gets its values from the other neurons. Like if you look at 0.1, for instance, it's getting all its values and weights from these other neurons. And those are also getting values, like for instance, this 0.3, like this, instead, this is like getting its values from these neurons. Do you see how it's all like a domino effect? So one thing I told you guys yesterday is garbage in, garbage out. One solution, if you're not getting good outputs, could be maybe your data is garbage. Maybe you've taken blurry photos of Obama, or maybe they're just not good enough. But if this is the only data that you have, like sometimes in medical data, like those are the only x-rays or chest x-rays that you have access to, then you have to work with the data that you have. But in other cases, you can work to try to collect good data, right? Like it's like maybe this is the only friend you have, and these are the only notes your friend took. So you're stuck with it. Okay, so I'm going to give you guys this short video to watch right now. I'll just be back in a couple moments.
Last summer, my family and I visited Russia. Even though none of us could read Russian, we did not have any trouble in figuring our way out, all thanks to Google's real-time translation of Russian boards into English. this is just one of the several applications of neural networks. Neural networks form the base of deep learning, a subfield of machine learning where the algorithms are inspired by the structure of the human brain. Neural networks take in data, train themselves to recognize the patterns in this data, and then predict the outputs for a new set of similar data. Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get activated or not. An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output is compared against the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs. This process continues until our weights are assigned such that the network can predict the shapes correctly in most of the cases. This brings our training process to an end. You might wonder how long this training process takes. Honestly, neural networks may take hours or even months to train, but time is a reasonable trade-off when compared to its scope. Let us look at some of the prime applications of neural networks. Facial recognition. Cameras on smartphones these days can estimate the age of the person based on their facial features. This is neural networks at play. First, differentiating the face from the background, and then correlating the lines and spots on your face to a possible age. Forecasting. Neural networks are trained to understand the patterns and detect the possibility of rainfall or a rise in stock prices with high accuracy. Music composition. Neural networks can even learn patterns in music and train itself enough to compose a fresh tune. So, here's a question for you. Which of the following statements does not hold true? A. Activation functions are threshold functions. B. Error is calculated at each layer of the neural network. C. Both forward and back propagation take place during the training process of a neural network. D. Most of the data processing is carried out in the hidden layers. Leave your answers in the comments section below. 3 of you stand a chance to win Amazon vouchers. So, don't miss it. With deep learning and neural networks, we are still taking baby steps. The growth in this field has been foreseen by the big names. Companies such as Google, Amazon, and Nvidia have invested in developing products such as libraries, predictive models, and intuitive GPUs that support the implementation of neural networks. The question dividing the visionaries is on the reach of neural networks. To what extent can we replicate the human brain? We'd have to wait a few more years to give a definite answer. But if you enjoyed this video, it would only take a few seconds to like and share it. Also,
Oh,
if
give me
you
one
haven't
second,
yet,
guys.
do subscribe to our channel.
This material right now. Did it make sense to you guys? Okay. So that's the same idea of a neural network, and how it works. So what happens is you make, you have an input image. You just randomly have your weights and you do a forward pass. And what a forward pass is sort of doing is it's going through the network and it's making a prediction, like, is this Obama, is this not Obama? It's making a prediction. And if the prediction is wrong, which it is here, it's wrong, then you're going back and you're making adjustments to the weights. That's what you're doing. You're reducing the loss by going back and making adjustments to the weights. You predicted Obama is 0.4 and now Obama is 0.6, but you actually wanted it to say 100% Obama and 0% not Obama. So what you need to do is we need to go back and reduce the loss by making adjustments to the weights. So that's what we need to do. We need to go back and make adjustments. And this is what Geoff Hinton came up with that we talked about yesterday. It's about back propagation, and it's making adjustments to these weights in order to get the output that you desire. So I think I will end here for today, unless you guys have more questions, but we'll finish this and review tomorrow if that's okay. Does that sound good to you guys?